Hi guys, Audrey here. So right now we're going to do an improper integral that has infinite bounds, that has a negative infinity and infinity as a bound. But more than that, it's also got an infinite discontinuity in the middle. So we've kind of got everything happening here. So I just want us to see what happens when that happens. Well, the first thing we know, so here are problems. The reason this is improper are the negative infinity, the positive infinity, but also that one right there. So we're going to deal with the one first. We're going to separate this at 1. So this is going to be equal to negative infinity to positive, I'm sorry, not positive infinity, to 1, 4 over x minus 1 times x squared plus 1 dx plus 1 to infinity of the thing. So at least now we can see that infinite discontinuity. The problem is we know that every improper integral is only allowed one problem. Right now I've got two integrals and both of these integrals both have two problems. That's not okay. So we're going to have to separate this thing again so that we have four integrals, all of which only have one problem. So the first one, we'll separate it at some value between negative infinity and 1. It can be any value we want. If I want to use 0.9, I can. If I want to use negative 84,762, I can. I'm going to use 0. So this will equal negative infinity to 0, 4 over x minus 1 times x squared plus 1 dx, plus 0 to 1, plus, now again, 1 to infinity, we have the 1 that's a problem, the infinity that's a problem. We've got two problems. We're going to separate this thing as well. I'm just going to separate it 2. Again, you can separate at any value that you want between 1 and infinity. So we'll have 1 to 2 of this thing, plus 2 to infinity of this thing. Good. So now we have four integrals. Each of those integrals has one problem each. So we're good. Now we can write these things as limits. So this is going to be the limit as t approaches negative infinity, t to 0, plus the limit as p approaches 1, and be careful here, because with infinity, negative infinity, we can really only approach one way. If I'm going to negative infinity, I'm on my way there like this. And if I'm going to positive infinity, I'm on my way there like this. That 1, however, I could be on the left side or the right side. Well, we're approaching from the left side because 0 is less than 1. So we're approaching from values that are smaller than 1. So don't forget that 1 from the left. That's actually important. We need that here. So then we'll say the limit as r approaches 1, 1 to 2, 4 over x minus 1 times x squared plus 1. And again, this time 2 is bigger than 1. So we're looking at that interval between 1 and 2. We're approaching 1 from values that are bigger than 1. So now we're going to have r approaches 1 from the right, plus the limit. And here we'll use an s goes to infinity. And I've done a little cursive s thing because I don't want the s to look like a 5. So from 2 to s of 4 over x minus 1 times x squared plus 1 dx. Awesome. So now we have these 4 different limits. We may or may not have to think about all of them, but we're going to start off by just taking the integral. So we're going to do the indefinite integral without the bounds, without the limits. We don't want all of that stuff in the way while we are taking the integral. So the indefinite integral. So we're looking 4 over x minus 1, x squared plus 1 dx. And what we see is that this is a rational function. The numerator has degree 0 because it's just a constant, so degree 0. The denominator has degree 3 x and x squared. So clearly no division is necessary. Plus the denominator is already factored. Which means we can go right into partial fractions. So we have 4 x minus 1, x squared plus 1. That x minus 1 is a linear factor that occurs one time. So it's just going to have a constant on top of it, that a. The x squared plus 1 is a quadratic factor that occurs one time. So it gets one fraction, but it has a linear polynomial on top of it. So remember, the numerator is always 1 degree less, with the assumption that we started off with division. So we've like eliminated the possibility that the numerator has the same degree or a higher degree. Good. Okay, so this brings us to our next step of these partial fractions, which is when we want to solve for the numerators. So we're going to multiply both sides of this equation by x minus 1 times x squared plus 1 to get that, that 4 is equal to a times x squared plus 1 plus bx plus c times x minus 1. Now I really only have one 0 here, x equals to 1, so we're going to start by plugging that in. X equals 1, which gives me 4 is equal to a, 1 squared is 1, 1 plus 1, plus b plus c times 0. So this gives me 4 is equal to 2a, a is equal to 2. Perfect. Now, I don't have any zeros left over, so I could move on to step 2, except that I haven't plugged in x equals 0 yet. So I'm going to go ahead and actually just stick to step 1 for the whole time. I haven't plugged in 0, plus I only have 2 things left to solve for. So we're going to plug in 0, and we're going to plug in a equals 2 at the same time. So x equals 0. To give me that 4 is equal to, instead of a, I'm going to write 2. 0 plus 1 plus 0 plus c times 0 minus 1, that's minus 1. So this gives me 4 is equal to 2 minus c. C is equal to negative 2. I meant to do that in black. C is equal to negative 2. Now, I can pick any other number that I want to plug in, because as I said, I'm going to stick to step 1, to method 1 the whole time. So instead of equating my polynomials, I'm just going to plug in negative 1. I could plug in whatever I want. I already know a and c, one thing left to solve for. So we're going to plug in x is equal to negative 1. So I'm going to have 4 is equal to a is 2. Negative 1 squared is 1 plus 1, so that's 2. Plus negative b plus c minus 2 times negative 2. So this gives me 4 is equal to 4 plus 2b plus 4. 2b is equal to negative 4. b is equal to negative 2. All right, so now we want to plug this back into the integral. So we get that the integral is 2 over x minus 1 plus negative 2x minus 2 over x squared plus 1. And so this is a form that appears at the end of partial fractions that we've seen numerous times. We know that to do this integral, we need to separate that second fraction into 2 different fractions. So we'll end up with 2 over x minus 1 minus 2x over x squared plus 1 minus 2 over x squared plus 1. 2 over x minus 1 is a known form. 2 over x squared plus 1 is a known form. The only thing we really have to think about is this, and the derivative of x squared plus 1 is 2x, which is just on top. So we're just going to really briefly do that substitution to show it. X squared plus 1 du is equal to 2x, so I end up with the integral of 1 over u du, which gives me ln u plus c, which gives me ln of x squared plus 1 plus c. Perfect. So now we're just going to apply our known forms plus that middle integral that we just evaluated with substitution. 2 ln of x minus 1 minus ln of x squared plus 1 minus 2 arctan x plus c. All right. I have now evaluated the integral. So let's just go back to the top briefly to see what we're going to do with this integral. We had 4 different limits. We're going to call the first one smiley face. We'll call the second one frowny face. We'll call the third one round face. And we'll call the fourth one asterisk. Okay, so we're going to start off by evaluating that first limit, smiley face. So smiley face gave me the limit as t approaches negative infinity of this limit that I am evaluating between, I'm sorry, not negative infinity, but t and 0. So first I'm going to plug in the 0, and this is going to be important to think about. So when we're plugging in this 0, the limit as t goes to negative infinity. I have 2 natural log of negative 1. We know that ln of negative 1 doesn't exist, but it's very important to remember that the antiderivative we got is the absolute value. So this is ln of the absolute value of negative 1, which is the same thing, as ln of 1. So that just equals 0. Then we have minus ln of 1 again. Then minus 2 arctan 0 minus 2 ln of t minus 1 minus ln of t squared plus 1 minus 2 arctan t. Now let's just remember here, arctan of 0 is equal to 0. If we need to look at a graph, we can. Pi over 2, negative pi over 2, those horizontal asymptotes. This is what our arctan looks like. It passes right through 0. Okay, so what that means is when we plugged in 0, we actually just got 0. So now we have the limit as t approaches negative infinity of negative 2 ln of t minus 1 plus ln of t squared plus 1 minus 2 arctan t. So when I plug in that negative infinity now, I'm ending up with ln of infinity, so this is negative 2 ln infinity, plus ln infinity, minus 2, well, arctan of negative infinity, that negative infinity right there, is negative pi over 2. Good. So what this gives me then is negative infinity plus pi. Problem. Infinity minus infinity is an indeterminate form. So we're going to think about just this part. That part right there gave me a pi, including that negative, gave me a pi. So then what is happening with this infinity minus infinity? Well, we saw when we were doing L'Hopital's rule that when we have a subtraction of lns, what we want to do is combine those lns. So we're going to use our 2 ln rules. Ln of a to the power of b is equal to b ln a. And ln a minus ln b is equal to ln of a over b. So, in other words, I'm going to start off by moving that 2 inside as a power. So, the limit as t approaches negative infinity of negative ln of t minus 1 squared plus ln of t squared plus 1 is equal to the limit as t approaches infinity, ln of t squared plus 1 over t minus 1 squared. Well, on the inside, because we're approaching infinity, we have that rational function, we can just take the big stuff. So the inside there is actually just going to 1. So this is approaching ln 1, which equals to 0, which means that up here, we actually have 0 plus pi, and our answer is that smiley face converges to pi. That's actually a bummer. We kind of wanted it to diverge so that we don't have to think about any of those other integrals. It converged to pi, which means we have to go on and look at the next integral, or rather the next limit. So our next limit was frowny face. Let's go up and look at it. Frowny face was the limit as p approaches 1 from the left with 0 and 1 as bounds. So, oops, my bad. So we're gonna go back down here, and now we're going to evaluate frowny face. So frowny face, we're saying the limit as p approaches 1 from the left of 2 ln of x minus 1 minus ln of x squared plus 1 minus 2 arctan x between 0 and 1. All right, so first we plug in 1, then we plug in 0. Limit p approaches 1 from the left, 2 ln of 1. Oh, sorry. I did that back wrong. That 1 is a t, my bad. T. So 2 ln of t minus 1 minus ln of t squared plus 1 minus 2 arctan t minus 2 ln of negative 1, but it's absolute value, so same as before, that's like going to 0, minus ln of 1 minus 2 arctan 0. All of these things here are just 0. So we end up with the limit as p approaches 1 from the left, 2 ln of t minus 1 minus ln of t squared plus 1 minus 2 arctan t. And when we plug in that 1 here, well, we end up with 2 ln 0. That's going to be 0 from the right because it's inside an absolute value. So no matter what, it's going to be approaching from positive numbers. Then minus ln of 1, then minus 2 arctan of 1. Well, arctan of 1 we know is just pi over 4. Ln of 1 we know is 0. And ln of 0 from the right, that's going down to negative infinity. So this is actually negative infinity. Yay! That's great. That means that we don't have to do the other two, because what we just got here is that frowny face diverges, which means that the whole integral diverges. The integral from negative infinity to infinity of 4 over x minus 1 times x squared plus 1 dx diverges for my final answer. Now, just a reminder of why that means it diverges, because we integrate from left to right. So what this is saying is when we get to 1, we're just going to be integrating forever because it's going, down to that negative infinity. So we're never going to get past 1. We're never going to have the opportunity to get past 1. So that means if one of the integrals that you get diverges, the whole thing diverges. So in this case, the answer is the integral diverges, and we are done. We don't have to look at the other two integrals we ended up with. That's all. Bye.